Hey, welcome to the podcast.
Thanks for having me.
I was reading about this Nobel Prize thing, and it's absolutely blowing my mind. There's this discovery about quantum effects in electric circuits, right? And I'm sitting there like, what even is macroscopic quantum tunneling?
Okay, so basically these three guys, John Clark, Michel Devoret, and John Martinis, they figured out something wild. They showed that quantum behavior, like the really weird stuff that happens at tiny scales, can actually happen in bigger circuits too.
Wait, bigger circuits? I bet quantum stuff only happened with atoms and stuff that's super tiny.
Yeah, that's exactly the thing everyone thought. But these guys pushed that boundary and showed it can happen at a much larger scale. That's why it's so groundbreaking.
Okay, so back up. What's quantum tunneling actually? Is it like the ghost through the wall thing people always talk about?
Exactly. So imagine you throw a ball at a wall, right? Classically, it just bounces back. But if that ball behaves like a wave, part of the wave can actually be on the other side of the wall already. So sometimes the ball just shows up there.
So it's like throwing a ball to the second floor, and even though you didn't throw it hard enough, it somehow appears up there anyway?
Yes, that's the perfect way to think about it. In circuits, electrons can tunnel across barriers they normally shouldn't be able to cross because they're acting like waves.
Hold on. Isn't that what a Josephson junction is? I think the material mentioned that.
Oh man, yes. So a Josephson junction is basically two pieces of superconductor with a super thin insulating layer between them. Martinez was doing experiments with these things back in the mid-'80s.
So this isn't brand new research, but the Nobel is recognizing like the deeper understanding of it all.
Kind of calm coherently across the entire circuit.
That's actually a perfect analogy. It's like a whole stadium cheering becomes one loud voice instead of thousands of individual voices.
Right, exactly. And because of quantum tunneling, current can actually flow across that insulating barrier without needing an external battery or anything. The voltage appears because of the tunneling and because the electrons are in these discrete energy states.
Wait, discrete energy states? Like in atoms? In a circuit?
Yeah, so they call it energy quantization. The circuit's energy behaves like a wave and ends up in these quantized levels, just like energy levels in atoms. That's the whole energy quantization part of the discovery.
So they basically proved two things at the same time, tunneling and quantized energy in a macroscopic circuit. No wonder it won a Nobel.
Exactly. And the big deal is that quantum mechanics usually only shows up at atomic scales, but these guys engineered it into something bigger that we can actually work with and measure.
So like, what does that actually lead to? I'm guessing quantum computers?
Oh yeah, the material talks about quantum computers that could solve problems in seconds that take regular supercomputers years, like analyzing someone's entire DNA or scanning stock markets. Crazy stuff.
The stock market example was pretty wild. Like, buy 20 shares and become a millionaire. I mean, it's over the top, but you get the point.
Right, it's just showing the potential. The real thing is that quantum circuits with these controllable states and tunneling effects form the basis for qubits, which are the building blocks of quantum computers. These Nobel Prize experiments helped prove you can actually engineer and measure this stuff.
So the material mentioned superconductors earlier. Why are those so important for all this?
Good question. So superconductors have zero resistance, meaning electricity flows through them without any loss or heat. That helps create really clean quantum states and keeps everything flowing coherently without noise messing it up.
So zero resistance means less noise and better coherence. So the superconductors keep those electron waves all synced up across the circuit.
Exactly. And that coherence is what lets the electrons act like one unified quantum object and tunnel across that Josephson junction.
The material also talked about particles acting like waves and vice versa. How does that fit into the bigger picture here?
So when a system behaves like a wave, parts of it can exist on both sides of a barrier at the same time. By engineering circuits where the superconducting current acts coherently, you get that wave-like behavior showing up at a larger scale.
So putting it all together, superconductors remove resistance, Josephson junctions let the quantum state tunnel, and energy quantization gives you discrete levels to manipulate. That's the whole foundation for quantum technology. That's actually incredible.
Yep. And that's exactly what the Nobel Prize name says. Macroscopic quantum tunneling and energy quantization in electric circuits. That's the whole achievement right there.
It feels like we just glimpsed into tech that could completely change computing and medicine.
Yeah, it's pretty wild stuff. We should definitely do a follow-up on how this actually gets built into real devices.
Thanks for walking through this with me, man.
Anytime. This is the good stuff.